All right, next we will have Sean Dettrick come up and talk to us a bit about computing at TIE.
Yes. Okay, thank you very much. So thanks for inviting me. I appreciate it. I'm going to talk today about a few things. My original title is to talk about exascale codes and how they can accelerate fusion energy research, and I'm still going to talk about that, but it was gently suggested to me that I could make it talk a bit broader. So I decided to include, wrong button, some information from our spin-off companies. So I work for TIE Technologies, which is a fusion startup company. And we spun off some companies in the medical industry and energy power storage technology. So I'll talk about those as well. And I acknowledge here contributions from my coworkers and from those sister companies. Okay, so TIE used to be called Tri-Alpha Energy. It's kind of the OG venture capital-backed private fusion company. We've been working for more than 20 years on this fusion concept called the FRC. And along the way of building a succession of experimental devices, we realized that we had developed a kind of very particular set of skills, kind of like Liam Neeson, right? And we can use those skills not to kill bad guys, but to cure cancer, potentially, and also kind of help to revolutionize power management. So I'll talk about those things also. But first of all, I'll talk about the fusion power results that we have. So why would you care about fusion? Well, I think that there's a very good reason. And our sources say the International Panel for Climate Change, Intergovernmental Panel for Climate Change, has this very complicated looking figure, which you can see up here. On the horizontal axis is about 1 century of time, and on the vertical axis is carbon dioxide creation. And you can see that we're here at the end of the black curve. If things go great, right? If we meet all the kind of policies which we all promise to each other in the various international meetings, we'll fit on this red curve here, if things go great. Currently, we're 1 degree Celsius above what we used to be about 100 years ago. If things go great, we'll only be between 2 and 3 degrees Celsius above the norm at the end of the century. So that's with current policy, right? So what we want to do is we want to try to lower that temperature that we're going to get to. And what these two curves on the bottom here show, if you can get to zero carbon output for the whole world economy, then we can limit warming to 2 degrees Celsius or 1.5 degrees Celsius. So we really need to revolutionize energy markets. So that's why we're interested in fusion. Now that was, as I was saying, in the kind of ideal case, we'll be stuck at 2 degrees. But it seems like energy demand is actually increasing. It's increasing, and within 30 years it may double, according to these projections. It's mainly due to increase in living standards in the developing world. And we can't just tell them to not have good living standards. So we really need to try to replace the energy sources with these kind of carbon-free sources. Fusion is one, fission is another one. There are other ones as well. But what is fusion? I should give you a little reminder, little recap. So fusion is when you take two different elements, two nuclei, and you bang them together, and they create a different pair of nuclei. In this case, you combine deuterium and tritium. They're two hydrogen isotopes, and you split them up, and you make a helium and a neutron, and it releases a lot of energy. Okay, so that's the kind of conventional fusion reaction, which most people work on in the national labs and in private industry. In our company, we're working on a different reaction, which is, has boron-11 and hydrogen. They collide, And after the collision, it's in a metastable state for a very short period of time, and then it splits up into 3 helium atoms. So the waste product of this reaction is helium, which you've probably breathed in at a kid's party to make your voice sound funny, right? So it's very safe in that primary reaction. For the usual deuterium-tritium reaction, which we're talking about, it's a bit complicated because of the tritium and the neutron. And for example, tritium has a half-life of 12 years. It's not available in nature. It has to be created. And the neutron, which is very energetic, is going to be basically destroying all the vessels, all the surrounding walls of the fusion reactor. So you need to actually create brand new materials for this type of fusion reaction. In comparison, the proton boron 11 or hydrogen boron 11, the fuels are abundant. There's a lot of boron that you can dig up out of the ground, and it's very safe. But the difficulty is you need to get to a much higher temperature. You need to get to 1 billion degrees, whereas deuterium-tritium, you need to be 150 million degrees. And for PB11, the engineering will be much easier, but the physics is less mature. And DT has the kind of opposite situation, where the physics is more mature, but the engineering will be more difficult. Now, at these very high temperatures, right, if you want to get to these extremely high temperatures, you can't just put them in a vessel because you'll melt the vessel or you'll quench your plasma, okay? So what you actually do is you put them in a vacuum vessel where the initial vacuum is like 10 to the minus 9 times the atmospheric pressure, and then you put very strong magnetic fields in there, and the magnetic fields actually confine the so-called plasma, which is a very hot gas, inside the vessel and keeps it away from the material walls. And these magnetic fields are created by currents, and there's many different ways of making those magnetic fields. You can have the currents entirely in coils, which are on the left-hand side, that thing called the accelerator. You can have most of the current in the coils, some of it actually running in the plasma itself, like the tokamak. And then if you continue along the spectrum, you end up with the FRC here, which has just simple circular magnetic coils creating straight field lines. And then there's current in the plasma closes the magnetic fields and makes it into an enclosed bottle. So that's what we're working on. That's called a field reverse configuration, or an FRC. And as I mentioned, TA has been working on this for a while, since 1998. It was at UC Irvine in California, and then it spun off into a private company. I joined in about 2002 on the C1 experiment. And at TAE and at any other fusion company or national lab, fusion devices are built in a kind of iterative design, build, validate, iterative process. And you have some theories, you design an experiment around it, and then you validate your theories, and you learn a whole bunch of stuff, and then you design a new machine, you build it, and then you validate, and so on. So we're at this green one here. We're at this so-called Norman validation period. And it's actually very expensive to build these things. Norman costs about $250 million in CapEx, right? We want to build this next machine. I don't know how much it will cost, but probably a little bit more. And when you want to try to reduce costs and also increase your ability to explore parameter space. So when you actually have a physical experiment, you can't just change anything that you want to on the vessel because the engineers have to get involved. You need to use a crane to lift the thing, and quite often you can't reach the parameters that you want to get because things are blocking each other. But in the simulation, you can change parameters any way you want to. You can create things which can't exist in the lab. And so if you have a very well validated set of simulation tools, you can actually explore parameter space, and you can design a new fusion reactor or fusion experiment just using simulation tools, and then you can build that new machine. Or you can, if you already have a machine, you can optimize the way that machine is used, or the way the experiments are performed on that device. So this is a picture, this is a kind of rendering of our existing machine, Norman. And you can see here there's a plasma here on the inside, and it's got these lines here, magnetic field lines. And these little blue things here are neutral beams. Neutral beams are being injected to maintain the current in the plasma. And this is how an FRC can be formed. There's different ways to form an FRC, but one way is to create two at the ends and bang them together like this, and then sustain them with neutral beam injection. that was kind of an artist's rendition, right? But we want to make actual predictive first principles simulations to demonstrate what's going on in the lab. And we've been working on that for some time. It's often called a digital twin, this type of thing, a first principles simulation. So we, inside TAE, we wrote in C++ this code which we called FPIC, which is a global stability code. You can see that this plasma is kind of self-organized and is able to rearrange itself in this way. So this is very interesting for us because we can control the way the plasma rearranges itself. So that's called global stability, where the kind of the wavelengths are large. And then we're also very interested in microturbulence. So turbulence causes transport. And so this is a different code, which is also developed at TAE in collaboration with UC Irvine. And you can see these very fine scale waves here at the edge. And then they actually, some shear flow creates, and then they actually form up into these larger structures. That's the inverse turbulent cascade, where tiny little fluctuations end up causing large structures, which can cause turbulent transport. And this code was also a completely separate code base for us, which was written in Fortran. Both of these codes use the OpenMP MPI hybrid paradigm of programming, and they scale very well on CPUs. We had this Insight Award on the Argonne National Lab Theta computer, which is a Xeon Phi system. And you can see, in order to get an Insight Award, we had to show that our code scaled well. So we showed each code could scale with a good, strong scaling up to about 500 nodes on the machine. And those results, as I showed on the previous page, were done using that kind of resource. But frankly, it's very tiring to develop two codes like that. We're only a small company. There's about 10 people in the simulation group, 10 to 15 people. It's very tiring, very difficult to develop this type of code. And then we developed it for CPUs. And then as we were doing it, the GPU revolution came in. And we weren't ready to go and essentially redevelop those codes ourselves. So what we want to do is we want to try to essentially collect a lot of different codes that we have and try to integrate them into one framework. So this microturbulence code, the global stability code, another fast particle code, a type of Monte Carlo code. And we want to, they all have shared features. They're all particle codes. They all use regular meshes, but the geometry is quite different, and there are other different requirements. But nevertheless, we want to try to integrate them all together into one code set. And so we decided upon some requirements. We want to have proven scalability on large clusters. It should be GPU capable. That's a kind of primary thing. We want it to have mesh operations and embedded boundaries if we can. We want it to have existing particle pushing routines, particle and cell operations. And we want it to be open source and have open source management practices and so on. So we looked around a bit, and what we found was the exascale computing project. Actually, I was attending to some of those exascale computing project meetings, and I just kind of discovered AMRX and WarpX accidentally. And it was developed at LBNL. So we selected these codes. WarpX is a code, I guess. AMRX is a framework. And then we started talking to these guys, and then shortly afterwards, they won the Gordon Bell Prize in 2022. But we knew them first, so before they became cool, just so you know. So we did start to adopt this and work in this framework. But I'll say a little bit about what that is. So David a moment ago was talking about the hardware aspect of the exascale computing project, the ECP. So we don't need the biggest computers on the planet. What we want is the best software and the fastest software on the planet. So part of the ECP project was this kind of huge investment in software, software kind of infrastructure, and then like GPU optimizations, and then linear algebra, and then sitting on top of that, other algorithms, and then sitting on top of that, physics algorithms, okay? So previously we were using PETSI and HDF5 and RDOS, But once we kind of discovered this stuff, we picked up AMRX and WarpX as well. So we're using these components. And the amount of things that we now need to represent in our own code is much smaller. We basically just need to write our application-specific information, and we're able to use the kind of existing meshing operations and particle operations. Okay, so we're using it as this framework, and part of what comes with it is this new community. They're not, I wouldn't say collaborators, it's too strong to say collaborators, but community members, people we can talk to, and they're helping to maintain the integrity of the code base, and we contribute our code, so we're developing code, and we can potentially use the adaptive mesh refinement components of AMRX as a kind of standard example of WarpX up there. WarpX was made, this movie on the top left-hand corner here, WarpX was really intended to look at laser wake field acceleration and advanced accelerators. So you have a laser going into a plasma, it entrains a wave behind it, and then electrons get captured in the wave and they can be accelerated to crazy velocities. And the time scales of such a simulation, the length scales are extremely short. But we want to operate on much larger time scales. So in this bottom ellipse here is supposed to represent the length scales and time scales. So this is length scale here, time scale here. The bottom ellipse is supposed to represent the typical time and length scale lengths of WarpX using the finite difference time domain. Okay, but we're interested in length and time scales which are 3 to 6 orders of magnitude bigger. Okay, so we can't just use the same algorithm. We can't run it for 10 to the 12 to 10 to the 20 times longer. Okay, it's already using some of the biggest computers on the planet. So we need to use we need to address the multi-scale issue by a hierarchy of models and by using new physics approximations and new applied math. Okay, and so one thing we've done is we've got a hybrid PIC model, which is a massless electron model, and we've refactored that into WarpX. And we're also adding new implicit methods. And because what we're doing is, we're developing sometimes called a digital twin. We're calling it a numerical FRC. It's like a first principles simulation of the device, which we hope will eventually become completely predictive and will enable us to help design new machines. So if you're trying to do that in plasma physics, in the old school days, which is not that long ago, a plasma physics simulation code would really only be inside the plasma. Most tokamak codes would be only inside the last closed kind of magnetic surface. But that thing is actually nested inside a physical vessel and has external actuators. So we want to include all the external actuators in it as well, and the interaction of the plasma with the vessel. So we're adding models for this type of stuff as well. So actuators include neutral beams. I showed that in that kind of cartoon earlier. And also we're including boundary interaction. And we have models for interaction between the plasma and the solid boundaries, which they themselves operate on different time scales. So you need to be able to integrate all that into one holistic model. And that's what we're trying to do. But so I'll just, when you do this, you want to use this in a predictive way, right? Once you have a model, you want to use it in a predictive way. And so to do that with confidence, you need to show that your model is predictive and it's correct. So that requires you to verify it against known theory. So I won't go into all this, but this is just to show that we have done verifications with our new hybrid PIC model. Some kind of classic plasma physics verifications here. Quite famous magnetic reconnection here on the right, which is something which occurs in the laboratory and in astrophysics. So we've shown that our new model does reproduce the correct results there. And then we're also, as I mentioned, adding new implicit models into WarpX. And this is a shameless plug for a poster. I have a poster today, actually. So after this, I have to go to the poster session. You're welcome to come and join me. I can give you a drinks ticket. We're showing in this poster, which again I won't go into detail, that our implicit model also is reproducing the theory correctly. Okay? So if we can reproduce theory correctly, the next step is to actually validate the code against the experiment, which is a much more complicated thing. But before going there, I'll just tell you what did we get out of this from a computer science point of view. Okay? So on the left-hand side, you see that blue bar. The left plot is a strong scaling plot, okay? And the blue bar is the time per time step of our previous global stability code, which is called FPIC. It was C++ code, OpenMP, MPI on the Theta computer. On 500 nodes, there are 30,000 cores, okay? So one 30,000 core simulation would run in one step would run in 5 seconds. Now on Perlmutter, with one node has 4 A100s. Each A100 has just less than 7,000 cores. So you've got just less than 30,000 cores on one node on Perlmutter. 4 A100. Almost the same number of cores as 500 nodes on Theta, right? And the time to solution on one node is the same as on 500 nodes. That's where we came between 2018 and 2023, okay? And then we show that if we increase the number of nodes, we have decent, strong scaling, but actually for us, we're more constrained by the size of the problem. We want a particular size problem, particular mesh size, and then how much resolution can we get? So for us, a weak scaling is very interesting. And so we show that the code has a pretty good weak scaling. If we continue to increase the number of particles and increase the number of GPUs at the same time, the performance actually slightly improves. And so the left bar, the leftmost bar on this plot compared to the leftmost red bar on the other plot, it's actually almost the same simulation, but you can see it's actually a lot faster. So what happened actually was, this is a benefit we get from using open source code. A lot of optimizations occurred in the open source code. One of them was, for example, GPU-aware MPI. So now when you're passing information through MPI, it doesn't have to go through the CPU, it just goes GPU to GPU directly. That saved a lot of time. And there's also a particle sort algorithm introduced. These things were introduced by Berkeley scientists. Nothing to do with us, but we get the benefit. So it's very helpful for us. Okay, so finally down to the kind of end slide on this. This is our latest and greatest simulation. This is a validation against the experiment. So you can see the red things there are coils. Those are the magnetic coils. The green lines represent the magnetic field, which is created by those red coils. And those kind of purpley-pinky lines, those are streamlines of the current density, which is created by fast ions, which are injected by neutral beams. So we're actually injecting current in the plasma using these beams, and the current in the plasma is maintaining the closed field line region in the middle, those closed green loops, and it's sustaining the magnetic configuration for many hundreds of alphen periods. And that correlates very well with what's going on with the experiment. And without this model and without this new neutral beam injection model and the equilibrium that we have, they wouldn't agree at all, actually. So that's a big step for us, and we're going to write a paper about that very soon. Okay, so that's it for fusion. And then I just want to talk about those other sister companies just very quickly. So if I can, okay. So boron-neutron capture therapy, what is that? So I was just talking about proton-boron 11 for nuclear fusion, right? There's a similar sounding reaction, which is neutrons against boron 10. And this can be used for nuclear medicine, where you collide a neutron with a boron 10, and then that has a reaction that creates a helium and a lithium. And why would you want to do that? Well, you'd want to do that, and the place you'd want to do that is inside a cancer cell. If you can get boron into a cancer cell and irradiate with neutrons, then that reaction will kill that cancer cell and almost nothing else, because those fusion products have a very, very short distance of attenuation. They dump all their energy within a few micrometers. Okay? So this gives us the possibility of a cancer therapy which is highly localized, okay, at the cellular level. And if you can deliver the boron 10 to the cell using some drug delivery, and you can deliver neutrons, then you can make this happen. So this is what our spin-off company, Life Sciences, is working on. And the fusion company have the expertise to build the neutron beam system and this beam shaping assembly, which I'll just talk about briefly. So this was all done, all kind of designed. Much of it was designed in simulation, but this is kind of the cool thing for me, which is this negative ion source, which then passes through an accelerator, and it gets converted to a proton, and then you end up with this proton beam going down these tubes here. It says neutron beam, but this thing is actually a proton beam system. The cool thing about it is with protons, they're charged particles, so you can steer them with magnetic fields and electric fields. So you can build one of these things in a hospital, and it can service multiple rooms. You can actually steer, you can have many of these beam lines going to different rooms, so you can have multiple patient rooms from the one system. Whereas if you want a neutron source, another way of getting a neutron source is to get a fission reactor and open a small door in it and stand next to it. That's kind of not ideal. So this is a lot better. And this stuff has been designed partly through simulation. So you can see here a simulation of the ion source where the electric fields are accelerating the ions. And then this is the accelerator, which takes the negative ion and then converts it to a positive ion, and so it accelerates in both directions. So it's kind of, this red thing on the right here is like the potential. You can think of it like a hill. So if you're riding a bicycle, you ride up a hill, it takes a lot of effort. Then you ride down the hill, you accelerate, right? What we can do here is if we change the charge on the ion, we can make it so when instead of going up a hill, it's actually riding downhill, and then on the other side, you change the charge, it's going downhill again. So it accelerates both ways, which would be pretty cool if you could do that on a bicycle. Accelerate uphill and downhill without pedaling. And then also, this is showing how you can steer the beam using magnets and various optical assemblies, and you can keep a nice straight beam path. And I should say that system, which was designed and built at TAE, is beginning to be fielded in hospitals. It's in a hospital in China, and hopefully coming to a hospital near you soon, or at least in your country. That's very, very early days, but it has massive potential growth capability, which kind of came out of our fusion efforts with some assist from HPC. Okay, and then I want to talk about another spin-off company, just very briefly, and it's a power management company, electricity power management. And it came from this issue that we have in the lab, that we built our lab in the cheapest real estate we could find, because you need a big space, right? And we only had a 2 megawatt power feed, but the experiment requires 750 megawatts. But it only needs it for a few seconds, every 5 to 10 minutes, but still 750 megawatts. So what we need to do is we need to pull in 2 megawatts of power and store it, and then be able to discharge all that energy in just about 2 seconds, okay? So to do that, we had to build this quite large and elaborate set of power supplies. But I think we're eventually able to arrive at one power module with an energy storage system and the electronics and the control system, and it's a network topology. And in the actual experiment, we need to be able to discharge those power supplies either from 2-second timescale down to kind of a few microseconds timescale. So it's very kind of heterogeneous requirements, different voltages, different currents, different timescales. And then some clever person, after we'd been doing this for 5 years or so, a clever person realized that that kind of heterogeneous power supply management that we'd developed could also be deployed in other places, such as electric vehicles. So we do have now this Power Solutions division, which is working on these technologies for electric vehicles. So we have like a battery pack with a control system attached to it, and they're talking to electric vehicle manufacturers and OEM manufacturers, and there's also UPS capability which we've developed as well. And just the finally last slide is these guys, going slightly back to AI, these guys who are doing this are working on a kind of optimization algorithm. So you can take into account weather forecasting, the state of your battery system, and you can bring in like government regulations. So you can look at carbon accounting, tariffs and so on, and market demand. And you can take all those inputs, you can put it into your optimization algorithm, and it it can operate your power supply system in such a way as to, make it cheaper, and also to help you with government regulations, so you can trade carbon balances and so on. So yeah, that's the plan that we're working on right there, and it seems to be also getting some traction in the marketplace. So thank you very much.
Great. Thanks, Sean. And I realized as I sat down that I didn't read your bio, so I will do it now just so you know who you were listening to. So Sean Dettrick has developed HPC simulations of fusion plasmas on a litany of now obsolete HPC systems, and having learned his lesson, now prefers to use high-level open-source libraries and frameworks to develop hardware-agnostic solutions. While working in private industry, he has been connected to DOE, leadership computing, as lead principal investigator on Insight and ALCC program awards, and as a technical representative to ECP's Industry and Agency Council. So Sean received a PhD in theoretical physics from Australian National University and worked at the Japan Atomic Energy Research Institute and the University of California, Irvine, before joining TAE Technologies, where he is now Director of Computational Sciences. So now you know why you were listening to him. So we have a few minutes for questions.
Hi, Dana O'Connor, Pittsburgh Supercomputing Center. So when you were looking at the scaling of the graphs, it looks like you were able to get some pretty strong scaling. So with some newer hardware coming out, do you see the limitation of simulations being more actual computations or mostly communications between different nodes?
I couldn't hear that very well, actually. I'm sorry.
Sorry, can you maybe, you may need to tilt the mic towards you. There you go.
Sure. So, basically, the question was with scale, see in the future hardware being more communication limited or computation limited, like the actual computation of the simulation?
Oh, okay. In our case, it's mainly computation. Yeah. So I didn't kind of mention that. So that big 3D simulation that I showed you, it runs on a kind of small number of GPUs, like 4 to 8 or 16 GPUs, something like that. And that run took about 8 hours to run on that type of device, on just a few, less than 10 GPUs. And that type of simulation has the scale, usually, of what we want to run in the current state. So the existing horsepower is good enough for us. But actually, I didn't mention, I meant to mention this. We actually have a plan to take not just that one run, but to do a kind of very large parameter scan with the code in a substantial data cube. And we have an ALCC award that's leadership, an ASCO Leadership Computing Award for about 300,000 hours on Perlmutter. So since that run took about 8 hours, we can do some, tens of thousands of simulations actually to explore parameter space. So for us, we don't need to go to extreme scale typically. Yeah, if we get more into turbulence, then we may need extreme scale. Yeah. Thank you.
Hi, I'm kind of curious how you made the leap from the boron-hydrogen nuclear fusion reaction to the cancer application of it. Was that made in-house by one of your scientists, they just realized it, or did you maybe publish a paper and a peer from the community, contact you guys with that correlation?
I'll be honest with you. I'm not 100% sure how that decision was made, but I believe that we actually had some external business people come in, and there was some kind of discussion, what can we use, how can we leverage our existing knowledge and technologies? And some business guys were looking at adjacent markets, basically. And because, the science people are very focused in their local niche, typically, and it's a different skill set to be kind of looking around at a more broad marketplace to see how your ideas, where parallel ideas can take traction, So we kind of had some external advice, I believe. And
then my other question is, I know you showed a lot of renderings, so I'm just kind of curious how far out with the boron-hydrogen reaction you would say you are to break even in terms of production of energy, because I know that it looked like it was more than 6 times more thermal energy required to get that ignition than the regular, the old traditional hydrogen-hydrogen fusion reaction.
Yeah, so that's a great question. So, how can I answer it? So I think somebody's going to be able to get fusion to work in the next decade. I mean, we can get the plasma density, temperature, and confinement time good enough to have a nuclear fusion reactor in the next decade. But can you commercialize it? That's the really hard part. So in the kind of the mainstream world, the tokamak world, I think that it'll be possible to build such a tokamak, such a device. But then nobody knows yet what materials to use in that device. Like what can your first wall be? Because your first wall actually gets destroyed quite quickly, and the cost of replacing it is higher than the value of the electricity that you create in that same time. So that's the main problem for that type of fusion. So there's a lot of money that needs to go into materials research. I'm not saying it's not possible, but that's kind of where the uncertainties are right now, is in materials research for DT fusion. For PB11 fusion, we don't have that issue. You can build a reactor with existing known materials. So we don't need really materials research at all. But we've been working on the plasma physics side for several decades less. We've been working on it for 20 years really with a lot of energy, and the DT fusion has been worked on internationally for 5-6 decades. So when will we be successful? I think that our next step device, after we build it, will really tell us how quickly. So we're going to build this next device to try to get to conditions which would work for DT fusion. But because of the materials problem, we're probably not going to build that DT reactor. But we want to show that we can reach those conditions. And then we're going to build the next step, which will be the PB11 reactor. So each one of those steps is at least 5 years, 5 to 10 years. Yeah.
Thank you.
So.
Yeah, so I actually have one for you. As you're, developing a new fusion reactor, how do you start taking huge data rates and feeding that into your simulations? Does that change the architecture of what you're doing?
Yeah, that's a very good question. So there's a whole section of this talk which I kind of deleted because I thought I was going to run out of time, and it was kind of about that. So we do have we have a huge number of diagnostics on the machine. We've got like 50 to 100 diagnostics, which create a gigantic amount of data with sampling rates 10 to the 6 hertz, very high sample rate. Huge amount of data, and we're feeding that data into advanced analysis programs, which we've been developing with partners, including Google AI. We had a good collaboration with Google AI for a while. So we're using Bayesian inference to kind of digest and process all that data to create a kind of state of the system. And then on the so that's of the experiment, right? And then on the simulation side, what we try to do is we try to have the same inputs as the experiment has, and then try to make a simulation which evolves in the same way, and then we can apply the same kind of synthetic measurements to the simulation, so we can compare the Bayesian inference reconstruction on the experiment with the simulation. Yeah, so it's not that the experimental data goes straight into the simulation. It's more like the two parallel systems. You try to get them to agree with each other.
Cool. Yeah, the digital twin idea. So,
yeah, exactly. Yeah.
Cool. Other questions? All right, let's thank Sean again.
Thank you.
And what I'm going to do now is ask Dave to come up as well, and we'll have just a little bit of discussion. And you'll find my hidden agenda for asking a car company and a fusion company to work together. I want the Back to the Future car with Mr. Fusion. And
I can see where this is going. Fusion propulsion.
Oh, yeah. Right? Back to the Future, right?
Yeah.
Right. That is the plan. Good. So, the first question I wanted to ask you is if you could wave your magic wand, what would you like to see from the Department of Energy and the computational science community that you're seeing here, that would help you in the, your individual companies, but also the communities that you're a part of, automotive and propulsion and fusion and healthcare? How would you change this if you were able to?
Oh, I'm actually very satisfied with the DOE. I mean, we do have access to DOE systems, which we've been taking advantage of. It's not easy to get access, but I think that makes sense. There's kind of a high bar to jump over to get access. But for the technical capability, I think is very good. Yeah. I actually can't say what I would like. What I would actually really like is to see somebody turn quantum computing into something which was actually useful.
Interesting.
For deterministic simulations.
Yeah.
Yeah.
So sorry, I put you on the spot on that
No.
question first, as I could think. So this last modernization in DOE went really well, so well. It's really well known by many that were a part of it or partook in partnerships, and then the transfer of the lessons learned. And actually other agencies, we didn't mention that. Part of this industry and agency council was so that all of these learnings around hardware and software and applications and integrations would transfer faster to all the agencies. And I think that was accomplished too. Mm-hmm. So everyone was in there, NASA and NOAA and NIH and DOD. As a matter of fact, Department of Defense was a co-chair. Mm-hmm. They were just on their path and starting their next modernization effort, and theirs was coming right after DOE. Mm-hmm. So in the next modernization, I think the ask kind of went to what was asked earlier, is how can we take that and build on top of it and continuously improve and see if we can do even better transfer of knowledge. Part of it is here. Mm-hmm. at the Supercomputing Conference. I think there's opportunity in a few other conferences where this type of information and knowledge can transfer. And then I think even in the technical paper and other forums where that information can kind of keep rolling in. So,
actually, I'd like to echo that. I remember now, thank you, that the knowledge transfer for me is one of the biggest difficulties. So I was going as a technical representative to the ECP meetings for several years, and what I was really quite overwhelmed by is the number of possible solutions to every problem. There's just so many crazy different ways of doing things, and it's very difficult to figure out what to adopt. And I was kind of lucky because I was kind of in that location, but I think that all the tools which have been developed, the software tools especially, which are kind of very, very broadly applicable, I feel like that should be advertised as much as possible. Because there's so many industrial tools and science tools which could be refactored into those tools to accelerate progress a lot. Yeah.
Good. All right, and maybe along those lines, DOE develops massive amounts of software. I know inside both your companies there's a lot of software development. Can you talk about your approach, how you decide? Do you do commercial? Do you do co-design in-house? Do you do community codes? And I think you both do all of the above, but talk about how you make the decision when you're looking at new software.
Yeah, okay, so in early days, we're kind of hobbyists and enthusiasts, so we tend to write our own code, right? And it's not intended necessarily when you write a code to keep it for 15 years, right? You usually think of it as being a 2-year project, but 15 years later you still have it, right? And you've got the 15 years of legacy, right? So that's kind of like, we've kind of realized that ourselves slowly, and then that's why part of the reason we're getting more into open source, kind of properly managed software. And it's more like, for us now, there's a balance between the open source and what should be kept private. And there are kind of good ways to run, like what we're doing with WarpX. It has a good Python interface, so we can make all the C++ code in the public realm, and then our kind of application-specific stuff is mainly in Python, and that can be kept in a private repo. So it's kind of public and private together in that respect.
So is there much of a Fusion community yet for community codes with other?
So there's always been some community codes, but there's always been some fragmentation. But we've noticed after we picked up WarpX and we put our hybrid pick model in there, we've noticed other companies, not Tokamak labs, because their tools are very good for what they want already, but other kind of non-traditional magnetic geometry companies have been picking up the same model that we kind of put in there. And yeah, so it's getting community traction in the kind of private industry.
I think we have all three. If we put them into three, there's probably more classes, but we put it into the commercial, what we've created custom, and then open source. And we leverage all three. I think that we lean into custom when there's something highly competitive in that area for a period of time. And then when it reaches a point where maybe there's others that are competing with us that have the same, and it's no longer a competitive advantage, we look to maybe even transfer it with a partnership into commercial, or even think about some open source model. So that's kind of been the thought process, where we are.
And I think especially for the automotive industry at large has really driven the commercial software as well. I mean, it's not an open source effort, but you're definitely affecting how ANSYS and Simulia and all do their code. So good. So if we have questions from the audience, I can't actually see there, but feel free to step up to the mic. If not, I have plenty of questions here too. I think, Dave, you're part of it. I am too this week, the mentor program. And so I've been spending a good bit of time giving advice that I'm not sure is accurate or not about where the workforce is going and what training you should have. I guess I'm curious about, in your companies, what are you looking for, and where do you think people who are wanting to go into high performance computing should spend some of their time?
Yep, I'll go first. There's a high demand right now, and for the foreseeable future. There are a number of people in the computing space around architecture, the actual hardware technologies, not only from the past, but now where everything's going, and then the software and integrations. And I know where I came from, where I am at now, there are people that are needed. And we see that in a number of other areas in other industries. They say the same thing. And it does take time also to become a little bit specialized in each one of those areas, especially in the high performance computing space. So it's a great area, high demand right now. And you can see that there are people that are seeking these individuals in all areas.
Yeah, that's good.
Yeah, so in our particular niche, there used to be, as I was saying, we're like the OG company, right? So there used to be just one private fusion company. Now there's 20. So it's become much more competitive to hire people. There's a much bigger job market. So I think that's very good for people who are kind of entering the field. They can actually work in different places. But when I think of what to say to somebody who's thinking of entering this industry or any other industry, I think doing an internship is really the best thing, because you can't really understand what's going on from the internet, But if you have the chance to go to a company and spend the summer there, or a NASA lab or a university, I think it's really the best way to figure it out. And during your student career, you can do multiple internships. You could do as many as summers you have. So I would really strongly encourage anybody to do that. Yeah.
Interesting. Yeah. So another question I have is about, you're both generating massive amounts of data. And when you start instrumenting cars and sensors and wheels and all, these are huge amounts of data. The people who are building these foundational models love this data. And it used to be freely available, and people shared it till they learned that OpenAI is making billions of dollars by training on the data. So can you talk a little bit about how you're thinking about the data and the expertise that you've built up around that data? And you're commercializing it or sharing it or building on it? Or?
Yeah.
So I'll start with data. We actually started breakfast this morning talking about the data storage and the volume of it, the size of the models, keeping it resident but high speed in one location because you need to be able to get at it, analyze, optimize, visualize. But then if you're moving large data sets around, that's costly in today's environments, or some, especially if you're thinking cloud. So that's a key piece. I mean, things that we feel are competitive, we're keeping in-house. And the storage and the movement of the data is a large part of our discussions right now. Yeah. And actually curating the data, like we mentioned earlier. For us, curating it, classifying it, having it in one spot so that we can use it as part of our learning libraries going forward, hugely important to us.
Yeah, yeah.
Yeah, it's a big deal for us as well. I mentioned we're trying to build a new machine, right? We basically spent a year discussing what data architecture system we should use. Because we were previously, until now, we're using the kind of usual fusion system, which is called MDS+. And that is great for storing data, but it's not very good, not as good for metadata. So for AI models, you want every single device on the machine, everything should be completely described, like every coil, every location, every calibration factor in every sensor, all that should be stored and machine readable. So when you build forward models for Bayesian inference or whatnot, everything is machine readable. So that's kind of, we made our own database for that. And then for the next device, we're looking for a new streaming data service, which will be cloud-based.
Yeah.
So but it's a big deal to try to figure it out. Yeah.
And are you thinking about, either one of you, monetizing this beyond internal use? Is it something that will become a revenue stream at some point?
For us, it has been discussed, but I don't think we know what to do yet because we first need to create it. But it's definitely been discussed.
Yeah, yeah.
So I'll say it. It's a partnership with the customer that we're creating and generating that data. So part of one division that I said, which is Ford Pro, it's actually one of the fastest growing businesses. The area of that business that is the fastest growing is around the data. It's not actually around the hardware and the vehicles itself. It's actually around the data.
Yeah.
And so this is in areas where you have fleets of people and vehicles and doing work. And it's what's being done and how it's being done and what we have sensors and what we're connected to and what we're be able to, look at and manage. So actually that is happening, but it's happening with the knowledge of the customer.
Yeah.
It's building that relationship and partnership and knowing, what we're doing with the data, and it has a purpose.
Excellent. Good. So I think we're kind of at our end of our time here. So let's thank Dave and Sean one more time. And I will let you get back to working on my fusion-powered car. So.
Will do. Yeah.
All right.
Thank you very much.
Thank you, everyone, for attending, and there will be invited talks tomorrow as well.